guys, in this video we're going to talk about deep learning. And yes, this video was created by Anshumaan Phukan. So, now do you ask why we need deep learning? So, if you're a dumb person, this graph will give you the simplest explanation. And for the others, you can refer to this book, which was written by these three experts. But if you're lazy like me who doesn't want to read any book, then don't worry, this is the video for you. So, let's start with the introduction, shall we? Deep learning, also known as deep structured learning or hierarchical learning, is a part of broader family of machine learning methods based on artificial neural networks. Learning can be supervised, semi-supervised, or unsupervised. For reference, you can take a look at this picture. Deep learning architects such as deep neural networks, deep belief networks, recurrent neural networks, and convolutional neural networks have been applied to fields including computer vision, speech recognition, neural language processing, audio recognition, social network filtering, machine translation, bioinformatics, drug design, medical image analysis, material inspection, and board game programs, where they have produced results comparable to, in some cases, superior to human experts. Yes, so many examples, right? No, you don't have to worry about it. Let's get on with the definition, shall we? So, the definition says that deep learning is a class of machine learning algorithms that use multiple layers to progressively extract higher learning features from raw input. For example, in image processing, lower layers may identify edges, while higher layers may identify human meaningful items such as digits or letters or faces. So, let's get on with the overview. Most modern deep learning models are based on artificial neural networks, specifically convolutional neural networks known as the CNNs. Although they can also include positional formulas or latent variables organized layer-wise in deep generative models such as the nodes in deep belief networks and deep Boltzmann machines. In deep learning, each level learns to transform its input data into a slightly more abstract and composite representation. In an image recognition application, the raw input may be a matrix of pixels. The first representational layer may abstract the pixels and encode edges. The second layer may compose and encode arrangements of edges, the third layer may encode a nose and eyes, and the fourth layer may recognize that the image contains a face. Importantly, a deep learning process can learn which features to optimally place in which level on its own. So, now you might be wondering, what does deep in deep learning actually means? The deep in deep learning refers to the number of layers to which the data is transformed. More precisely, deep learning systems have a substantial credit assignment path known as the CAP depth. That's really deep. So, to explain it more easily, you can take a look at this picture. So, our next topic is going to be interpretation. Beware, it's going to be confusing. Deep neural networks are generally interpreted in terms of the universal approximation theorem or probabilistic inference. The classical universal approximation theorem concerns the capacity of feed-forward neural networks with a single hidden layer of finite size to approximate continuous functions. In 1989, the first proof was published by George Cyberbenko, but for Sigma activation functions, and was generalized to feed-forward multi-layer architects in 1991 by Kurt Hornig. The universal approximation theorem for deep neural networks concerns the capacity of networks with bounded width, but the depth is allowed to grow. The probabilistic interpretation derives from the field of machine learning. It features inference as well as the optimization concepts of training and testing, related to fitting and generalization respectively. More specifically, the probabilistic interpretation considers the activation non-linearity as the cumulative distribution function. The probabilistic interpretation led to the introduction of dropout as regularizer in neural networks. So now, it's time for the history. Yes, you might be wondering, isn't deep learning a new topic? Don't worry, I'm here to guide you. So for starters, you can pause the video and take a look at the entire deep learning timeline if you want. It's done? The term deep learning was introduced to the machine learning community by Rina Dacher in 1986 and to artificial neural networks by Iger Eisenberg and colleagues in 2000 in the context of Boolean threshold neurons. The first general working learning algorithm for supervised deep feed-forward multi-layer perceptrons was published by Alexei Ivanenko and Lepa in 1965. A 1971 paper described a deep network with 8 layers trained by the group method of data handling algorithm. Other deep learning working architects, specifically those built for computer vision, began with the neocognition introduced by Kunihiko Fukushima in 1980. In 1991, such systems were used for recognizing isolated 2D handwritten digits, while recognizing 3D objects was done by matching 2D images with a handcrafted 3D object model. The real impact of deep learning in industry began in the early 2000s when CNNs already processed an estimated 10% to 20% of all the checks written in the US. According to Jan Lessoon, industrial applications of deep learning to large-scale speech recognition started around 2010. In 2010, researchers extended deep learning from timid to large vocabulary speech recognition by adopting large output layers of the DNN based on context-dependent HMM states constructed by decision trees. Advances in hardware enabled the renewed interest. In 2009, NVIDIA was involved in what was called the Big Bang of deep learning, as deep learning neural networks were trained with NVIDIA graphics processing units known as the GPUs. That year, Google Brain used NVIDIA GPUs to create capable DNNs. Now, let's begin with applications of deep learning. Automatic speech recognition. Large-scale automatic speech recognition is the first and most convincing stressful case of deep learning. LSTM RNNs can learn very deep learning tasks that involve multi-second intervals containing speech events separated by thousands of discrete time steps, where one time step corresponds to about 10 milliseconds. LSTM with forget gates is competitive with traditional speech recognizers on certain tasks. Image recognition. A common evaluation set for image classification is the MNIST database dataset. MNIST is composed of handwritten digits and includes 60,000 training examples and 10,000 test examples. As with Timid, its small size lets users test multiple configurations. A comprehensive list of results on this set is available. Visual art processing. Closely related to the progress that has been made in image recognition is the increasing application of deep learning techniques to various visual art tasks. DNNs have proven themselves capable, for example, of A. Identifying the style period of a given painting, B. Neural style transfer, capturing the style of a given artwork and applying it in a visually pleasing manner to an arbitrary photograph or video, and C. Generating striking imagery based on random visual input of fields. Now, there are many other examples. Let's begin with them. CRM, known as the Customer Relationship Management, Recommendation Systems, Bioinformatics, Phone Advertisements, Photo Reconstruction, Natural Language Processing, known as the NLP, Drug Discovery Toxicology, and many, many more. Now, we are here with the commercial activity. Many organizations employ deep learning for particular applications. The Facebook AI Lab performs tasks such as automatically tagging uploaded pictures with the names of people in them. Google's DeepMind Technologies develop a system capable of learning how to play Atari video games using only pixels as data input. In 2015, they demonstrated their AlphaGo system, which learned the game of Go well enough to beat a professional CSGO player. In 2015, Bleeper demonstrated a mobile augmented reality application that uses deep learning to recognize objects in real time. In 2017, Covariant AI was launched, which focuses on integrating deep learning into factories. From that time, we're praising this new technology like anything, but we haven't spoken anything about its spooky consequences. Yes, it's a cyber threat. As deep learning moves from the lab into the world, research and experience shows that the artificial neural networks are vulnerable to hacks and deception. By identifying patterns that these systems use to function, attackers can modify inputs to ANNs in such a way that the ANN finds a match that human observers would not recognize. For example, an attacker can make subtle changes to an image such that the ANN find a match even though the image looks to a human nothing like the search target. Such a manipulation is termed as adversarial attack. In 2016, researchers used one ANN to doctor images in trial and error fashion, identify another's focal points, and thereby generate images that deceived it. The modified images look no different to human eyes. Another group showed that printouts of doctored images then photographs successfully tricked an image classification system. One defense is reverse image search, in which a possible fake image is submitted to a site such as TinEye that can then find another instances of it. A refinement is to search using only parts of the image to identify images from which that piece may have been taken.
I'll be back.